and welcome to a second last topic of digital elevation models and application course. And in this topic we are going to discuss the Viewshed analysis, and also we will be covering about the how flood hazard mapping can be done using digital elevation models. If you recall the previous discussion when we have been discussing about how to use digital elevation models in solar energy estimations, there also we have discussed about the viewshed, but that viewshed is hemispherically upward looking viewshed. Here it would be looking, this viewshed analysis is based on the horizon, that means parallel to the surface of the earth. So that's the major difference. Of course, there will be some other differences and options which are going to be available when we go for viewshed analysis, and also we will be discussing where viewshed analysis can be applied in our engineering applications. Also, sometimes in the literature you may find a different term which is also called visibility analysis. So instead of viewshed, one can also call visibility analysis. So what we are going to discuss here, that what is viewshed basically. Viewshed is the identification of areas of terrain using a digital elevation model that can be seen from a particular point on the surface of the earth. So this is what a viewshed is. We may determine a viewshed in a particular direction or maybe a 360 degree. We may add some offsets to the target, maybe offset of the person who is going to look from a point or a height of a tower. All these things we will be looking. So in this, like in this example, on the right side what we are seeing, this is the location of a point from where the viewshed analysis was done in the terrain, and if we restrict that only on one side I want to analyze, then these green areas are showing that from this point these green areas would be visible and the remaining areas will not be visible from that point. Because if you see very carefully, you would find that this point is located on the slope which is roughly north facing, and therefore southern facing slopes and all those sides will not be visible at all. So this is what the identification of areas of terrain that can be seen from a particular point on the surface, and this is what the example is. We also see that in viewshed identifies the cells, because it is what we are employing is a digital elevation model which is a raster based. So it identifies the cells in an input DM that can be seen from one or more observation locations. In viewshed analysis, you can also involve not only one observation location but multiple observation locations as well. So through a point file, that information can be provided along with offsets and other things, and then a combined viewshed analysis can also be performed. And this operation, the viewshed operation, involves of course a digital elevation model which is the main input here, or a digital terrain model, or maybe a tin. So on tin also, which is another terrain surface representation, can also be employed for viewshed operations or analysis. And this viewshed, when we use a DM to calculate viewshed of a particular point, what we basically require that the location of that point, so XY location, and then of course what is the height, and so we can add that one. So in this, like a point X can be seen from surface Y, maybe a target location is there, and what part of surface Y can be seen from point X. So if I can see a point Y from location X, then I should be able to see the same X from Y location. And the multiple point viewshed can also be combined to calculate the viewshed of line and areas, and where when the part of feature X can be seen from on surface Y, and what part of surface Y can be seen from which point on the feature X. So, when we involve multiple points, then analysis becomes little complicated, but does not matter. This can be achieved quite easily. Only the interpretation part may be little confusing when we involve the multiple observation points. So, while calculating this Viewshed, a line of sight from the observer point to the terrain surface is calculated, and which search the intervisibility matrix through which it calculates the intervisibility matrix, and visible parts of the terrain surface. As an example, I have shown earlier that some parts of the terrain were visible from that particular location, and non-visible areas or dead areas can be assigned a different color, and this we can, as mentioned earlier, that we can add a offset of the terrain offset from the observation point, because if a person is standing, then his height can be added as offset, or if a person is standing on a tower or building, top of a building or roof of a building, then the height of the building can become offset. So, that offset is also added, and if it is related with some turbine or some other thing, that height can also be added. If we see the example here, that what we see here, that a person is having offset A is located here. There are persons which are having offsets B. So, we can analyze along this is of course a profile section, but we see here that the person A can see partly the person standing in this NV area or on the top of the hill, that person can fully see, but the person who is behind this hill cannot be seen by this even offset or a person standing at this hillock. So, this is without offset B. If we do not add the offset B, then this is how the analysis NV not visible, here not visible, and this part is not visible. And whereas with the offset B, when we are having that offset, then entire from this location, that means from this location up to this location, the entire area is visible, but except this part, that is the other side of the slope, which is not visible. And this is of course an example here with the offsets in a 2D or just along a profile, but when we imply digital elevation model, we can see all around, not only along a profile, but all around. Maybe as per requirements, we can go do this analysis for 365 degree as well. So, what are the parameters which control or input which are required while doing the Viewshed analysis? As mentioned, these offset A and B, that means observer and target offsets can be there, and then we can restrict the azimuth, that only in between this azimuth and like in this example azimuth 1 and azimuth 2, I want to analyze the Viewshed or create a Viewshed, and then I can also restrict the vertical angle, that how above from horizon it will look. So, that horizon is here. So, this vertical 1 and the vertical 2 can also be incorporated, and then radius, that what is going to be the radius of that area which one would like to analyze. So, involving these kind of inputs, one can determine a Viewshed as per desired or as per requirement. So, it is possible to limit the region of the raster or DM, which is inspected by specifying various items as or various options as given or can be provided through attribute table. And for example, observation point elevation values, vertical offsets, and horizontal and vertical scanning angles, and scanning distances, how far the analysis is required. Maybe end of the boundary of digital elevation model, or if you are covering a very large, or if you are analyzing a very large digital elevation model, then you can restrict the distance that scanning distance is only that much required. This is the example of Viewshed analysis along a line, as a line of sight you can say, and on the same DEM which we have been using in this course, the example DEM. And if a person is standing here, the line of sight has been drawn like this, then these are the areas which would be the green areas which would be visible or part of the terrain. However, in this line of sight there are areas marked red which will not be visible. And of course, this is a hillside just to bring the terrain and relief undulations, so that this viewshed has been overlaid, or rather in background the hillside has been kept. And so here we like in simple analysis we can provide the observer offset, and that would be in the units which your elevation model is having for vertical scale. So this is 5 meter, and then target offset is given 10 meter, and then analysis is performed. And of course, in the profile also you can see the same analysis, that this is the line of sight visibility profile. So these red parts cannot be seen, whereas then green part, this is that corresponding green part is seen. Then again you don't see a small patch of the terrain as here marked red, and then a large part, and the green part is shown here, then again a red patch, and then finally a green patch. So likewise, plan view can also be seen in a line of sight as well as a profile. But when you are going for a 360 degree, then only in one particular direction or along a line of one particular direction you can have this profile. Otherwise, only in case of a line of sight this profile can be determined. If we go for a Viewshed analysis along a single point in a circular fashion, and by giving this radius, what we have restricted, that the distance it has, scanning distance it has to cover is as per the radius given here, the point here, and the areas which would be visible are all shown in the pink color, and rest of the areas will not be visible from that point. So likewise, such a analysis can be done only along a line or in a radius, or depending on. Now here the input parameters, the offset was again kept 5 meter, a target offset was 10, field of vision, that means it has to look all around, that means the 360 degree. One can also restrict to say 100 degree or 90 degree or 180 degree depending on the requirements, and less the degree we will keep, quickly the analysis will be done by the system, and near distance how close you want and how far distances it should cover. So all that can be given as options, and once the analysis is done, such outputs can be created. We will see some applications also. So instead of having a circular approach, one can also have a rectangular approach, that I want only the visibility analysis in this particular rectangle whose center is here. So the observer is here, and then again the red areas from that point which is light blue color cannot be seen, whereas the green areas are only seen. Here also is a different tool in ArcGIS, and this visibility analysis again brings some options here: offset A, offset B, azimuth 1, azimuth 2, vertical 1, vertical 2, and all these options are available for our analysis. Similarly, Viewshed analysis can also be done for entire digital elevation model, inputted digital elevation model. So we can do the Viewshed analysis along a line, that is line of sight. We can restrict in a particular direction, we can restrict and under a circle whose radius we can decide, or a rectangular, or even for entire digital elevation model as shown here. that the observer is here, and then submitted for entire area. So, red areas are not visible from this location with that particular offset which was given here, whereas the green areas are visible in this one. So, multiple examples can also be added, and multiple observers can also be added, as one can see here that a Viewshed has been done for 5 observers here. So, again, as convention is that Viewshed analysis has been done. So, the low visibility or rather no visibility for the red areas, green will be the visible from these points, and the range is there between 0 to 5. This means that if a yellow color is coming, that means roughly from 2 or 3 locations that area can be seen, or 2 observation points. So, that is why there is a range between 0 to 5. 5 means from all 5 observation points, that area that is shown here is as green color can be seen, whereas complete red means from no other remaining points, means 4 points or no points, that area can be seen. So, there are 5 observation points, and suppose this is the area which cannot be seen by any of these observation points. So, 5 means the terrain, part of the terrain can be seen from all observation points, and 0 means from none of the observation points. And if we want to just classify and between visibility and non-visibility instead of a range, like here in this legend is telling us between 0 to 5, we want just a sort of binary, that visible and not visible, then this analysis can also be performed like this. So, only if visible from any point, then it will be considered as green. If it is not visible from all points, then it will be considered and none points, then it will be considered not visible. So, not visible part is little less compared to, whereas green area, that is visible part, is maximum, because 5 observation points, and the classification has been done based on just visible or not visible. So, once the output has been created or a Viewshed has been created, then we can classify in that case when we are involving more than one observation points. And there are some other examples also there. There are 2 types of visibility analysis that can be performed here also, that the 2 observers are here in this example. We see only the visible part, whereas with the same observer locations, but we want to see which one are visible from, which part of the terrain is visible from observer 1, which part are of the terrain are visible from observer 2, and which part are visible from both the observers. So, all 3 possibilities are also there. So, this can be also analyzed like this. So, this frequency means this determines that from how many locations a part of terrain is visible. So, frequency determines which raster surface locations are visible to a set of observers. If we are having 5 observers, whether it is visible from 5 locations or 3 or 2 or 1, whatever. And observers, it identifies which observers are visible from each raster surface. So, the analysis has to be done from both ways, as given in the beginning, that a location X should be visible from Y, and vice versa is also true, because it cannot be one way. The visibility will always have the direct connection. Now, when we are doing this analysis for a terrain, or when large distances are involved, and therefore, when visibility analysis being done over a large area, then 2 other parameters will play a very important role, and one is the curvature of the earth and another one is the refraction, and these corrections then have to be performed if our line of sight is very long, or if our search area or a scanning area is very large, because if it is there, then these 2 parameters will play very important role, and if the corrections are not incorporated, then the analysis will not be very reliable. So, the Viewshed it will generate may not be very reliable. So, use of earth curvature correction option to correct the curvature of the earth and refraction, and now with the modern GIS softwares, these options are becoming now available. So, we don't have to basically program the things, but now only thing we have to understand that how much correction will be required and so on and so forth. So, if I take the example of line of sight, then observer offset is 1, consider is say in meters, and the target offset do not have any, so it is a 0, just surface, and when we apply for earth curvature, then these are the values which when we opt for that, then these are the values will come in the default for refraction and earth radius correction for radio waves and others, and when we go for applying this thing, we get the correction performed. So, corrections are made when projection information for surface is present, and that means that the digital elevation model has to be projected in some map projection. If it is just in degree decimal non-projected situation, then such corrections of earth curvature and refraction cannot be incorporated. So, one has to remember this thing that the corrections are made only when the projection information for surface is present, or the digital elevation model has been projected in some projection system, maybe say UTM or polyconic or whatever. And in addition, the ground units and surface jet units must be in feet, meters or unit meters. That means both units, horizontal unit and vertical units should be the same, and the formula used for this correction is something like this, that Z actual, that is the height, Z actual equal to Z surface, which will come from digital elevation model, minus distance 2 and the diameter of the earth, and then plus refraction factor multiplying by distance 2 divided by diameter earth. So, with this correction, we can perform a more reliable Viewshed analysis for when large area or longer, very long line of sight is involved. These refraction or curvature of the earth are very important in case of targeting some missiles and other things, because these missiles travel for very long distances, and therefore refraction and earth curvature plays very important role. So, these when these are the distances, distances are mentioned here. So, distance, the planimetric distance between the observation feature and observed point, diameter of the earth, refraction, this refraction is the refractive coefficient of the light, and the default value for diameter of the earth is defined this much meters, but when it is projected, then accordingly it will be taken. So, and this coefficient is 0.13 is taken, and that is why in this here 0.13 has already been taken in this to apply for refraction correction as a default value. So, when involving this thing, our visibility analysis may be little different, but if area is large, then only we see much differences while involving earth curvature correction and refractivity refraction correction. But for a small area, probably we may not see much differences if we incorporate these corrections. So, this is visibility or viewshed analysis for a terrain area. Again along a line, this is example from digital elevation or TIN, triangulated irregular network, on which also we can perform the same viewshed analysis. This is the example here, that this is the observer location, this is the target location, which part would be visible in which are given in green color, which part will not be visible are given in the red color. So, the input can be either your digital elevation model, that is raster, or can be tin also. Now, this is the example how one can perform in ArcGIS, and when I choose all these things, I have to give this is in line of sight. So, I am giving a direction and a target location and offset and other values, and once you do it, then you get this kind of analysis. For example, here only a small part of the terrain here which is visible, rest are not visible, because if offset has not been added, much offset has not been added, then there are chances that the through visibility analysis you would find that only a very small path along a line of sight is visible, and same would be in case of if I go for a rectangular or a circular area. So, offset has to be added. Generally, some offset, at least human height, has to be added. If one is targeting from the top of a building or a tower, observation tower, then that offset has to be added. Now, how other these corrections play very important role, as we can see that here let's assume that an observer O is located at sea level, that is looking towards the target here, that AT, located again at the sea level. And now earth curvature, how it is playing important role. So, for the calculation we will assume the earth is a sphere, but you know that for perfect calculations few more parameters have to be incorporated, because earth is not a perfect spheroid. Nonetheless, for here we are assuming that earth is a perfect spheroid, then let's get the radius r, that is the earth of the earth at the observer O and at the target location here also at AT. Now, the radius of the at the target will intersect the tangent at observer at point T here. So, this indicates the sink of the target, instead of here it is coming here due to curvature of the earth as S. So, this S factor has to be incorporated. So, using Pythagorean theorem, we can easily obtain the value of the sink, how much drop is there, and that is R plus S square equal to R square and D square. And likewise we can calculate. So, this can be solved for S as a quadratic equation, and then we get the the value of the S, which is D square by 2R plus S. So, for different distances, this has this sink, how much sink effects will come or drop effect will come, has been calculated for 1 kilometer, 5 kilometer, 10 kilometer, 30,000 kilometer, 50,000 kilometer. These number of meters, the sink would be there. So, it plays very important role for the sink, and only this correction or such corrections are required when large distances are involved in our calculations in Viewshed analysis. Also, a little bit about how atmospheric refraction will play important role, as we can see here that these different atmospheric layers which surrounds the earth, we are having the position of the sun, actual position of the sun, but because of refraction effect we get the apparent position of the sun somewhere here. Same way our observations or in Viewshed analysis, instead of getting the actual position, we get the target position, apparent position, something like this. So, atmospheric refraction is the deviation of light or other electromagnetic wave from a straight line as it passes through the atmosphere due to variation in air density as function of a height. So, when it passes through different layers, it bends and the position is somewhere else. So, taking into account the refraction of the light, as a general atmospheric condition, the density of air decreases as height increases, and as a result of this, the lights tend to bend as it travels long distances through air, and this causes distant objects near the horizon to appear higher than they are actually are. And instead of feeling here, you may have a feeling that the target or the height of that location or point is much above. And this negates to some extent the sinking caused by the curvature of the earth, but not fully, so that the refraction coefficient might differ for different atmospheric conditions. But since we do not have regular availability of such values, so 0.13 can be taken in most of the cases. So this refraction coefficient, this is how it is derived. Now there are examples of Viewshed analysis or line of sight analysis with the different sinks are there, and that compared with the profile of the surface with the increase of the distance to the observer. So how things are changing here, as you can see very well here, that observer is here, and then what we see, the changes in the visibility part of that, as one can see very easily here. So if we change the distances, and the sinks will affect, and therefore we will have a different Viewshed analysis. Here in the first example, there is no difference, and whereas when we add a few more things, then the difference becomes large, as you can see. So the green part here of the surface will be visible along this line of sight profile, and the red parts are not visible, and the effects of the curvature can be seen here. And this is the line of sight of radio propagation, and this is the effect of atmospheric refraction. So these factors, curvature and refraction and changing atmospheric conditions, may bring some changes as depicted here. Otherwise, we may get analysis something like this. So actually that analysis should not have been like this for Viewshed, there should have been like this in this one. Now what are the applications of visibility analysis? There are various applications. One mainly for observations or locations one can use that for visual impact analysis. Somebody is going to construct a tower or building or something, and before that they would like to see that how much part of a valley or hill would be visible from top of that building or from the window of different floors. They can analyze. Also when somebody is constructing these observation towers, maybe in a forest area or maybe in a mining area or for security purposes or for telecommunication, then this Viewshed analysis can play a very important role. These mobile operators nowadays are using Viewshed analysis to see the level of signals which would be available in the target locations. Also we can involve in landscape evaluation, that how things are visible and they can be organized, and this also, as I have just mentioned, the siting of observation towers, which is going to be the best location for such towers or cellular communication mast or towers, that can be done, and we can model these coverages of cellular communications or mainly mobile communications. Of course, military applications are there. I have given the example related with missiles and other things, where these corrections or errors have to be taken care, especially curvature of the earth and refraction and changing atmospheric conditions. If that much data is available, then live analysis can also be done. And virtual GIS also, where these flight simulators and other things are done, where also in those analysis, the visibility analysis is going to be very, very important. This virtual GIS was developed on war footings when we had this Kargil bar, and digital elevation models were employed, and top of that then latest satellite images were draped, and then pilot were trained before they were dispatched for the site, so that this virtual GIS can help, and also in that one this Viewshed and all these things, and this is not exhaustive list, so there can be many more applications of visibility or Viewshed analysis. And this is one of the examples of how Viewshed analysis in on Mars it has been done, because human cannot reach. So when somebody or some equipment is being sent, so one would like to assess what would be the Viewshed for that equipment. So this Mars exploration rover MER project, and this USGS used a Viewshed analysis to assist this Mars explorer, that when it lands on the surface of the Mars, which area would be visible, which will not be visible, and how it will be doing the exploration part. So that that was done in advance, because digital elevation model of Mars was available, so Viewshed analysis could be done. And when this we want to find out, or NASA wanted to find out the appropriate landing spots for Mars rovers, they turned to the USGS map for the best possible sites. Basically, the USGS maps of Mars, and part of analysis included a Viewshed of possible site selections, and in this case the Viewshed indicates the areas which may not be visible for Mars rovers from each landing site. So different sites were evaluated, and the most appropriate site was finally then selected for landing of this Mars Explorer rover. Now in the last very briefly I will touch how digital elevation model can be used for flood hazard monitoring, planning and other things. As you know that digital elevation model is representing the undulations of a terrain. So along a flood plain of a river, that can also be utilized. It can be simulated that if water level in a river goes to this level, then how much area would be inundated. This kind of simulation we have discussed when I was discussing dam simulation. So almost the same tools can be used along a river valley or across a floodplain, and we can instead of assuming a dam, we can assume a water level, and then we can simulate or model that how flooding would occur if water level in a river goes like this. So this is then one of that example here given, that this is purely DEM based flood monitoring or flood planning rather, and that this geomorphological processes that are active in floodplain areas are, as you know, that related with the terrain, especially fluvial geomorphology I am talking, and DEMs are the most suitable data for such kind of analysis, and we can perform not only the qualitative but quantitative analysis, that where exactly the area, which areas would be inundated, how much water would be there, and so on and so forth. And historical elevation data if are available, then sedimentation and erosion rates may also be derived from digital representation of relief over space. So if a flood has happened in past, we want to estimate that how much sediments, fluvial sediments it has created, how much erosion was there, what was the rate. Probably these things can also be calculated, but for which probably we may be requiring several successive digital elevation models, maybe in time series. So this longitudinal profiles can also be drawn, and cross profiles can also be drawn, and a plan views of through a digital elevation model of inundated area can also be drawn. So this DEMs can really help not only for the Viewshed analysis of different types as we have discussed, but also related with the flood hazard monitoring, planning, and similar kind of studies where terrain data is involved. So this brings to the end of this discussion. Thank you very much.